So I'm going to continue my to give the second lecture. First of all, I would like to remind several key points of the techniques that I described the previous lecture to be prepared to see the proofs. There are four ways about the matrices of that form, and let me skip immediately. So what do I need? I need the notion of the resolvent. I need the uh, resolvent identity. Then I need the spectral theorem. And we have immediately from the spectral theorem seems all the eigenvalues are real. We have this bound. Uh, okay, excuse me, the bound. In general, we have the bound for arbitrary remission matrix. We have a bound 1 over imaginary part of Z, but if the matrix is positive definite and eigenvalues are also positive, we can confine ourselves to the just negative semi-axis, and then we have more convenient bound, which I am going to use. Then I'll need the trace one perturbation formula, and especially this bound for the difference of traces, provided again that the matrix A is positive definite, and the perturbation parameter tau is also positive. Then we have this bound, which we are going also to use, and there is very important property called intermittency, that if you just have the Hermitian matrix A with eigenvalues lambda 1, lambda superindex A, and then you add, oh, excuse me, please, you add the perturbation of that form positive, then all eigenvalues of B are shifted to the right, but not too much, just to be between each one between eigenvalues of the unperturbed matrices. It's called intermittency, and the important consequence that the number of eigenvalues of, oh my God, this is A and B. This is misprint. Eigenvalues of B and A that are falling in any given interval delta of real axis, they differ at most by 1. Well, and I'll need the notion of weak convergence of measures. Okay, we have a measure, again, for simplicity, it will be positive measure with support on a positive semi-axis and non-negative for any set. And the important thing that the total mass is 1. It's called P measure, probability measures. And if we have a sequence of these measures converging to a certain measure, then we have to, and we have a continuous function, bounded continuous function, then we have to interchange the limit and the integration, and it is in all books. Okay, and one more property is that if we have an infinite family of these P measures that are tight, that means that the uniform bound for the tails, then there is also a subsequence in this infinite collection, oh my God, such that converges to a certain limit. It could be many sublimits, and in fact, our goal is to prove that all of them, they coincide. Well, in the case of matrices, yes. Then we need an important tool, which, by the way, was discussed at the end of previous lecture, and I am grateful for the person who asked this question because it's very pertinent question. So it turns out that it's very hard to deal with directly with eigenvalues. They are not quite nonlinear, complicated functions of the matrix, of its entries. And it turns out that quite efficient tool, you have to pass from the eigenvalue distribution to its Stieltjes transform, which is defined on that way. And we have this is just, you go from the measure to the Stieltjes transform, which is a function of complex variable, analytic outside of the support of the measure. And we have an important inversion formula that given a function, a CTS transform, we can find the measure by using this formula. And even more important, equally important, that this correspondence one-to-one between measures and CTS transform is continuous if you use in the space of analytic function the convergence on certain compact sets and the property that the limit is satisfies this condition, and the weak convergence of measures. So it's one-to-one correspondence, which is continuous. So if you have this, if you put here for f a new, a certain sign, a certain index in the collection, then you can make limit on this in both formulas. Well, and you find much more in the book by Naomi Heather. And one more thing that I need, it's if you have just quadratic form, quite simple, you have a matrix, you have a random vector, and you know this random vector has independent components satisfying this condition, then the expectation of the quadratic form is just the 1 over n trace of A, and since this form, this vector y is random, the form is random, and the variance of this random form, which is, by definition is the square of expectation of square minus square of expectation, is bounded or norm of the matrix squared and 1 over n. So it vanishes with a certain constant here. Well, next thing that we will need, it's called the martingale bounds. So if you have a, wait, I don't know why. If you have a, no, not here. If you have random variables, independent and normalized by the way that is written, I don't know why it is normalized expectation 0, and there are certain moments, then, and you have a function of m variables. M is a number of our random variables, and if you form this random function by this way, there is a jargon of statistics, they call it statistic, a certain function of a given random variables. And if we denote, so I remind you that xi's, they are independent. Because of that, we can make the expectation separately with respect to each variable integrating. You have m random variable, we can integrate any of them, some choice, not all of them. If it is all of them, we denote just E. If it is just with respect to 1 and up to the alpha size, then we denote this in that way. And in that way, we see that if you have this definition, f subindex phi subindex alpha, then phi subindex naught is our random variable, and phi subindex m is just its expectation. And then we just write this difference, just adding, subtracting the same. We can write in this form, it's just a trivial algebra, and the quite non-trivial, then we form the variance of this random variable, it is here. And of course, it's again simple to write this formula because you have this sum of deltas, you take sum squared, you single out the diagonal summation and the rest. And the quite important observation that despite that now these phi alphas, they are dependent random variables, you still have the bound similar to that in independent case. Yes? So we have not a bound, but just this identity. So the variance, or just, the second moment of the centralized centered phi is given by this sum. And it is quite non-trivial things because you see that this expression, it is just superficially, you see that it is of the order m squared because there is double sum. But no, it is just m. And you can proceed that you can write something similar by using this formula. You can try to find the force moment here, and okay, it's certain argument. You'll find that you have a similar bound, which we are going to use also. Well, and after that, okay, what we are about uh, now, we are passing for our problem. We have an infinite collection of these random variables that we wrote as a okay, double infinite, infinite, semi-infinite matrix. Okay, better to say the table. And then we have these properties, and we take the upper left corner of the size Mn, and we view it as a matrix. Yes, now it's just matrix of finite size. And if we need that, we need another matrix we call Rm, M by M, which is diagonal with eigenvalues tau alpha. Yes, and we assume that if we write the counting measure of these taus and divide by their size, their number, we assume that when m tends to infinity, this is just a measure, yes? Atomic measure. It consists of isolated points of atoms, yes? So it converges to a certain measure, and with m tends to infinity. Every time when I'm going to mention convergence of measure, it will be always weak convergence. Well, and by using this ingredient, we form the matrix is here. Previous time I forgot this important factor. So we take a rectangular matrix. Yes, it's transposed. Then we write Rm, and as a central, we write the X. This will be positive definite matrix, and therefore it has certain eigenvalues which I denote in that way. And by the way, I would like to repeat that it could be in principle eigenvalues no, of which coincide, so multiplicity not one, but I count all of them, always. And as I said before, taking into account that our matrix is X is random, in fact, it is quite highly unlikely to have the coinciding by eigenvalues, but nevertheless. So, and I form again, this time, this is eigenvalue counting measure of the matrix in question, yeah, Mn. And our goal consists of two sub-goals. First, we would like to prove that this random measure, because the matrix is random, eigenvalues are random, then we would like to prove that this random measure converges with probability one. So that means for every realization of our infinite random collection, with probability one converges to non-random limit, which we denote nu m, in this double limiting transition. We have two integer valued parameters that characterize our matrix M and N, and we assume that they both tend to infinity, but in the asymptotically proportional way. Yes, so we would like to prove that this limit exists, that it is non-random, and very important to characterize somehow efficiently the limiting measure. Well, and this is a theorem which I am going to prove. And in addition to the conditions that I mentioned before, x alpha j, the expectation is 0 and the second moment is 1. Now I assume that fourth moment is finite. And this is condition for my axis. And second condition for my matrix Rm, subindex M, I assume that this sum is uniformly bounded in M. So again, you see, I impose two conditions, one of them on X, second one on R. Now I would like, under these conditions, I would like to solve, excuse me, I would like to solve the problems that I mentioned in the previous slide in red. So I would like to prove that the eigenvalue counting function converges with probability 1 to certain non-random limit, which is also a p-measure. the normal total mass 1, and I would like to prove as a characterization of the limit, I would like to prove that if I pass from the measure to its TTS transform, then it solves this functional equation. It is equation because f is here and f is here. And you can forget about the origin of this, that it is TTS transform of certain measure. You just assume that this, we are looking for the solution of this equation, for the unique solution in the class of non-negative function and subject of this condition that uh, this limit is 1. Well, this is a theorem. And now just a remark that in fact we can consider a more general matrices. It can be the matrix of that form. Okay, you have the same random X, you have non-random R, non-random RM, and N and 0. The only thing that you assume about these two non-random matrices, this is that okay, each of them has you can write for any Hermitian matrix, you can write its eigenvalue counting measure normalized. They are denoted as new M not N and new RM, and we assume that they converge weakly to new node and new R, not necessarily matrix RM is not necessarily diagonal and positive definite, just any Hermitian. And under this condition, and I do not require that the force moment of the entries of X is finite. It suffice to assume that it is just second moment is okay, is finite, and we normalize it to 1. And then the limiting measure, again, if you pass from the measure to its TTS transform, it is solution of this equation. This time, we are looking for the solution in the class of analytic functions that are analytic outside of positive semi-axis. They have this property that imaginary part of f times imaginary part of its argument is not negative if imaginary part not 0, and we assume this condition. So we have this our answer given in that form. Well, and now let us pass to the proof. And the first, maybe there are questions. It's good moment to ask questions concerning the problem itself. Other
Right
questions?
now, there are no questions right now.
Okay, let's go. Let's proceed. Well, at the first step, quite important, by the way, of the proof, we are going to prove the proposition which is formulated here. If we have the same matrix, if we have, if nu mn as before, as denoted before, its eigenvalue counting measure, yes, then, okay, it's random variable, random measure. We can, since it is random, we can, of course, make expectation. Okay, again, it's mistake, misprint. This should be bracket, not just parenthesis. Yes. So you have what is here? Just the standard thing. You have a random variable. You subtract its expectation, and you are interested. What are the fluctuations? So you expect there is expectation, there are random fluctuation around the expectations. So it is just we would like to prove that the probability of these fluctuations vanishes in the limit. When n tends to infinity, again, excuse me, please, here, there should be two things. Okay, they should be. Well, and it is probability 1, this random variable tends to 0. That means that fluctuations vanish at the limit. Yes. And what is the proof? I'll start the proof by writing quite useful form of the matrix. Let me remind that the matrix as it is defined, it's here. You see, it is in that form, the product of three matrices. Now I would like to write a bit different, quite useful form. Okay, I'll denote the column of the matrix X by x alpha. This is definition. So it is just a column. These are random vectors. Yes. No, this is not a column. This is a row. Excuse me. Yeah, it is written here. Yes. Yes. And I would like to normalize them in that way because of this normalization. What does it mean? That I pass from x to the x divided by square root. Yes. And this is a column of that matrix y alpha, capital alpha, and we can easily check that the the components of that row, they are independent and normalized on that way. Well, and if we introduce these vectors, then you can write it if it is the matrix form, the entry is a sum over alpha. It is just matrix product, interpreted in that way, times 2y's. Or if you remind yourself the definition of rank 1 rank 1 matrix, you can treat this product as the matrix elements as the entry of the rank 1 matrix determined by y. Yes, it's important. Or okay, this is just in the form of I gave here the form of, so it is form coming from that because R is diagonal. Yes, but now it is my interpretation, and I just would like to stress this interpretation writing in just the whole matrices. So I I show you my matrix Mn, which is written the sum of rank 1 operators L y alpha, and having written in that form, I can take any alpha which is in that sum, any term, and single out of the term and write my matrix. It's trivial observation, and you will see that it is quite helpful. So I write my matrix as a matrix where this is just notation. In M alpha, there is no X alpha or Y alpha. And this particular term, which I singled out, yes? And an immediate consequence of that, you see these two matrices, MNL alpha, they differ by rank 1 projection. And recalling this intermittency property, we can write that does we take any interval of the real axis support of the measure, and if you take the difference of eigenvalues falling in delta by matrix Mn and matrix Mn alpha, they differ at most by 1 over n. Because, let me remind you, the number eigenvalues by intermittency differs by 1. But my measure, eigenvalue count, normalized eigenvalue counting measure is the number of eigenvalues falling in delta divided by n, by the size of matrix, yes, size. This is why we have here not 1 by 1 over n. And now recall our martingale type bound, but fourth order. This I am rewriting that for your. So we have, if you take now, just if you take, just remind the construction. You have a certain number alpha m random variables, and there was a remark: our random variables, they are not necessarily even just okay, they just assuming values on the real axis, they could be random vectors, even random matrices. Therefore, what do I do? Let me just show you. So we take that formula, we take the statistic phi, our eigenvalue counting measure, we take as xi alpha, now it will be a vector, not like in my example, which is in tutorial when xi was a scalar. Yes, and then we write this delta. Let me, okay, delta is just the difference, sorry, the difference, what is delta? It is just the difference of, you take your random variable, your statistics, you take the expectation with respect to alpha minus 1, xi's or y's, and alpha. Yes, you take a difference. Oh my God. What is going on? Just a moment. Here, yes. So in our case, we put as a phi our new. So we write, this is just a definition of delta. Yes. Now, see, I just, because my random variables size, which are now y alpha, they independent, I can write, this expectation as the expectation of with respect to 1 alpha minus 1 and last one. So I can write this expectation as a product. I put out of the brackets the expectation with respect to 1 alpha minus 1. Then here will be new m and itself, but and the expectation with respect to alpha. Yes, and it is quite important next step. I can now add is subtract mu m and alpha because of what? Here it is nothing. Okay, I can put anything. I can subtract anything. But why I can put this my things that I'm adding is subtracting it, under the side of E alpha? Because by definition, M and alpha doesn't depend on Y alpha. So we can write this identity, just equality, not inequality. So we have this. Now we apply for every difference, this one and that one, yeah, our this inequality, intermittence, yes? And therefore, each of these terms is bounded just by 1 over n. And now our delta is bounded just by 2 over n. And then by using this bound written here, we easily obtain. So from the bound, you have a sum. Under the sum, you have delta alpha in the fourth degree. Therefore, you have 16 over n4, n power 4. And there is m, and there is a sum, because delta alpha, this term, it doesn't depend on alpha. So it gives just one more m. And you obtain m squared over n fourths. But we know that these two parameters are proportional. What does it mean? That means that our statistic, this important deviation characteristic, so you have mu m, which fluctuates, and its expectation, we take the fourth moment of fluctuations, and you see that they vanish quite fast. Oh, it's again a mistake, minus 2 here. Well, so we have this property, yes? And what do we do? If you have fourth moment, we use standard trick of probability theory. We can, excuse me, we can write Chebyshev inequality for this deviation, yes, and you see that this corresponding probability decays as the n minus 2. We use Borenko-Antevy lemma. I believe that it was explained at previous time. If we get our proposition. I remind you, propositions that this quantity converges with probability 1 to 0. So the fluctuations vanish. This is the third assertion on the way to prove the theorem. Well, okay, other questions?
Are there any questions?
Well,
No.
well, let's go. Now we pass. So what is our goal? Let me repeat. Our goal to prove that mu mn converges with probability 1 to a certain limit, yes, which is non-random. At the moment, we prove that mu mn minus mu m, its expectation converges to 0. If we will be able to prove that expectation converges to a certain limit, not random, it's much simpler, then this result, our proposition plus our would-be proof that expectation converges to a limit will give us the first assertion that mu mn converges to a random limit. So the problem, this proposition reduces the problem to the analysis now, of, just a moment, to the analysis of the expectation. So we have to now occupy ourselves by the expectation and to prove that it converges to a certain limit. This is all. This is what we have to do after the proving this lemma. Yes, this proposition. Yes. Okay. First of all, the observation is that this sequence of these measures. This is a sequence of measures. So this sequence is tight, consists of tight measures. I remind you that we say that the sequence of measure is tight if the probability for each of them to be okay to be small for the intervals that are just near infinity is small. So in the jargon of probability, we say that the tail probability is small uniformly in n. Yes, but it is easy to find because let's compute just the first moment of our measure. Yes, because of expectation is linear operation, integration also, so by just Fubini's theorem, you can interchange these two operations, and then it will be just expectation of the first moment of the measure itself, not its expectation. But by definition, our eigenvalue counting measure, and by spectral theorem, this interval is nothing as just the n minus 1 trace of Mn. Yes? Now we compute trace by using definition of our matrix Mn. The trace will be this sum, double sum. It is just matrix. And then let me remind you that the expectation of we again now it's finite sum. You can easily put the expectation inside the sum, and then the expectation of every x alpha j square is 1. So we are left with the sum, and this is our condition 2, that this sum is uniformly bounded in M. Yes? Well, so the sequence of measures which we are going to study is tight. Yes, and because of that, and let me remind you that there was an assertion which is called in all books in probability called first heavy theorem, that if you have a family, an infinite family of probability measures, of p measures, then there is always a subsequence which converges to something, yeah? To something, yeah. So, but of course, we are not satisfied in that. We would like to prove that all the sequence converges, but at least we have something. We know that there is a subsequence that converges. Well, and now we would like to prove that this limit is unique. We know that there are sublimits. Maybe there are many sublimits, yes? If you take the number 0 and 1, there are two sublimits, yes? At least zeros and 1, and there are many others, yes? But our goal is to prove that nevertheless, all the sublimits, whatever is their number, they coincide. And this is what we are left to prove. So to this end, I am going to pass from the measures, as I mentioned, as I promised before, to their TTS transform. Let's start from the measure itself, not its expectation, but the measure, and let's denote its TTS transform in that form. It is just the definition which was already mentioned before, yes, in the tutorials. And yes, and I know that my measure, the matrix is positive definite, therefore its support on the positive semi-axis, and this is why I can write safely integral between 0 and infinity. Yeah. Now let's just okay. No, it's what is going on? Here. Yes. Now we need not the Stieltjes transform of this measure itself, but we need just Stieltjes transform of its expectation. Therefore, I just take this definition and just apply expectation to the both sides by using Fubini's theorem again. And yeah, I obtain that expectation, which I will denote Fn on Z, it is by definition, and it is a what it is an analytic function outside of positive semi-axis. So I would like to prove. You remember that there is one-to-one correspondence, which is continuous, by the way, between the measures and Stieltjes transform. Therefore, instead of proving that there is a limit of expectations, we could prove that there is a limit of these functions, analytic functions. And since they are analytic, I believe that you know that if there is analytic function, it is uniquely determined by its values on any compact set of complex plane. So I will choose as a compact set just the interval on negative semi-axis, and it suffices to prove that there is a limit, there exists a limit on this only for the values of argument on a certain interval on negative spectral semi-axis. Well, and so now we reduce the problem to this assertion, yeah? Now, what I'm going to do, I would like here the place when I would like to pass from the Stieltjes transform to the resolvents. Yes, let us recall that by so what is it resolvent? It is this matrix. Yes, it is well defined because outside of the spectrum of ends, that means everywhere in that set, in the complex plane with a cut or positive semi-axis. And now I will use spectral theorem and write the spectral theorem and write the resolvent in that form. Now, if I need the 1 over n trace, recall, here we need 1 over n trace, yes, G. So I apply to this equality, I apply the trace, okay, normalized trace, and this will be this sum. And by definition of the measure, it is just the Stieltjes transform. And this is very important argument because it makes the root from the measure which you're looking for to its Stieltjes transform, and from its Stieltjes transform to the resolvent, to the trace of the resolvent. So we have Gn is written in that way, Fn is expectation, and we have to study now the expectation of this normalized trace for the Z varying on that set. And to this end, so it is one more, let's repeat, it is presented here. Yes, it is presented here. So our goal now is to study. So this is what we would like to find. So the limit of that, we passed to this point, and now we are going to try to find the limit on the t in the interval of this expression. And now we will deal with the resolvent. Yes, what is it? Okay, I write the resolvent identity. So it is trivial algebra. I take two matrices, 0 and our Mn, and write resolvent identity, which was written in the tutorial for any two Hermitian matrices. Now one of the matrices is 0, and if you have, let me show you, if you have resolvent and your matrix is 0, your resolvent is just minus 1 over Z. This is why I wrote in that form. Okay, it's a bit physical way to write. I have to write, in fact, in front of Z minus 1. It is just complex variable. I have to write the unit matrix, n by n unit matrix, but I do not write, yes. Well, this is just trivial algebra. Now I recall that my matrix is a sum of rank 1 operators, and I can rewrite in that way. I remind you, this is notation for simplicity. I denote L subindex alpha, my rank 1 operator. which we wrote this representation for Mn several slides above, yes? And now we have this expression. Now it is still not too useful, but now I use the rank 1 perturbation formula for Gn. And you can easily see from that formula that if you take rank 1 perturbation formula between Gn and what? And Mn alpha, the matrix in which you just put given tau alpha 0, then it follows immediately from the rank 1 perturbation formula that the matrix Gn, yes, can be written as a matrix Gn alpha, which is a resolvent of the matrix Mn alpha. There is a quite nice formula, so that form, and here we have just new function which is explained here. So I repeat once more, Gn alpha is our G where you just assume that tau alpha is 0. Yes, here is Gn alpha multiplied by that vector. And okay, you can ask me where does it come from? It comes from when you take Gn alpha L alpha and the trace. Yes. Well, if you use this expression, now I would like to put this right hand side of this expression here, and I arrive to quite interesting and important identity. It is still identity, nothing else. Is just a bit sophisticated linear algebra. And you arrive that relation. Everything is defined. I repeat, L alpha is just the rank 1 perturbation corresponding to the row number alpha. Our matrix Gn alpha is a resolvent in which this row is omitted, and you have the things the resolvent which you are looking for here. It is expressed via the resolvent in which in each of them we omit the term alpha. Yes. And now since I need the normalized trace, so I apply to this identity the operation 1 over n trace, and next. And I arrive to this relation. It is still identity. It is still identity which expresses my function fn that I'm looking for, yes, via something else, via function ha. Yes. Okay, what is the time? I have still, Anya, how many minutes? 5 or 15?
25 minutes.
25? But there are questions.
It's time with questions, yeah.
Okay, so let me finish in 15 minutes to have an hour, and then we will leave 15 minutes for questions, if any.
Okay.
Well, so this is just, I repeat, this is nothing else as linear algebra, nothing else here. Okay, but I promise you that by using this relation, I'll prove the theorem, yes? And now I would like to justify my promise. Assume for the moment that we can do 3 steps. Okay, in fact, the one step, but I would like to assume for the moment that we can replace Hn alpha by Fn. Don't look on these 3 formulas, it will be. Then we can rewrite this relation via Fn. So it will be already not identity, but a certain equation. Okay, would be, because there is still error term if I am right, and you have to pass to the limit. But this important step, I would like the main step of the proof, it is convenient to divide in 3 parts. First of all, I pass from H alpha n, here is its definition. I would like to replace this quadratic form by n minus 1 trace of the matrix Gn alpha, which determines the form. Next step, I would like to get rid of from a subindex alpha. I would like to pass from Gn alpha to Gn. So this will be the same trace by the matrix, by the full already resolvent, yeah? And third step, I would like to pass from Gn to its expectation. Provided, so all these three steps sum up, okay, would result at the moment to this replacement. Now let's proceed. Assume that I am I am able to do all these things resulting in this replacement to arrive to this equation. Yes, what is next? Then let's look. Well, you can easily see that Fn here, and the sum Fn doesn't depend on alpha, so I can just rewrite this relation with a bit of course, the work on that form. So I solved roughly this, okay, I just transformed this equation in that form. And of course, it is still not exact because previous relation had the error term, and you can easily check that the same term will be here. Not the same, but the same order of magnitude, yes? So we can rewrite our relation in that form, yes? Well, and now what we are going to do, we have two problems. We have n, we have m. Our goal is to carry out the limit with respect to both these indices, yes? Assuming that they are asymptotically proportional one to another. So let's start from n. So uh, there is a theorem of complex analysis that if you have a sequence of analytic function, then there is a subsequence of these functions that converges on a certain compact of complex plane. If you do not want to recall this theorem, you can just remind this what did I say before? I said that the measures which we are considering, the expectations, they are tight. That means that there is a subsequence of measures. You can take subsequence of measures and use the continuity of Stieltjes transform, and you see that if there is a subsequence of measures conversion, there will be subsequence of their Stieltjes transform that converges. In any way, if you agree that there is such a subsequence, then you can pass you can pass to that limit, okay, keeping that at the moment, yes, and you will have this relation because there is still, okay, I am not passing in fact to the limit n because I have to do it simultaneously, but just I am replacing Fn by F, okay, calculating the error term, which is here, and I have this formula, yes? And in that formula, we can recall the definition of the counting measures of tau alpha. It is just by recalling this definition of that new Rm, you can rewrite this relation in the form. You have this. Here is the definition. This is a counting measure of tau alpha. Yes, normalized to have a total mass 1. So yeah, I can write this expression in that form just by definition of nu. And then our condition number 1, our theorem is that this measure converges weakly to a certain limit. So I can pass to the limit, and I am arriving as a result to this equation to the Stieltjes transform of the subsequence of measures, of the limit of subsequence of measures, yes? So it is subsequence of Stieltjes transform. So what did we prove? We proved that whatever is a sequence of Stieltjes transform, the subsequence, there could be many, each of them satisfy this equation. So in principle, this equation could have many solutions, and then it will be okay, it will be disaster for us, but we are going to prove that this equation has a unique solution, and provided that it is proven, we are done. We will prove that indeed there is a limit. Well, let me pass to this to the last slide. So what I'm going, so first of all, we can assert that our limit satisfy this equation. It is just the limit in the CTS transform. Yes, we have this relation, and it is more or less simple, but for us important that, okay, it is our function is positive because I am looking, as I said, the near equation here, yes? So, and the second, and quite important, that this equation, that equation, it has a unique solution. Okay, let's assume that there are two solutions, standard way, yes? What does it mean? There is some amount, some number, maybe continuous, maybe discrete, of values of argument for which, okay, minus is here, for which these two functions do not coincide. Let's write the equation for the both of them is subtract one from another. We'll get this relation because we assume, okay, in fact, just subtracting, we will get relation in which both sides of this relation, they are multiplied by the difference f1 minus f2, but it is not zero. So I can omit, and I have this relation. So left-hand side is 1. But okay, right-hand side is written here. We know that all f's are positive, tau is positive, therefore we can replace the both factors just by 1. And what did we get? We get as a denominator, we will have tau squared, f1, f2, but they are here. Therefore, we proved that the right-hand side is strictly less than 1, while the left-hand side is equal 1. Therefore, this contradiction proves that the solution is unique. And well, the theorem is proved modulo 3 assertion that I just tried to convince you that they are indeed valid. So now, provided that what is our left job, the last job, we have to prove that this replacement, which we wrote as a step of threes, yes, 3 steps, 1, 2, 3, okay, 2 steps, but 3 relations. So they are indeed valid. So if we will be able to prove these 3 okay, asymptotic relation, asymptotic replacement 1, 2, 3, then the theorem will be proved. Okay, I'll stop here, provided that maybe there are questions. Yes?
So thank you. Any questions now?